Okay, welcome. This is the Mobile Embedded Devices seminar number 2, and we're going to look at using cross-development tools, and specifically we're going to be looking at cross-compilation because this is a really key area for you to understand. Now, if you've been used to using an IDE, an integrated development environment, up to this date, you'll find that your knowledge of compilation is possibly fairly limited. You click on a button and it either works or it doesn't. Now, when it actually comes to compiling for cross-development, it's more or less impossible to use that level of tool, and you have to understand the actual lower level tools much more intimately. Partly this is because all of the systems are quite bespoke and quite different, and also because you're quite often trying to optimize the code for things like battery usage and speed and size and so on and so forth. Now this slide here shows us the bit in the box in the middle is the command, so CC, quite often, most times for C compiler, that might be GCC, and this is typed from the command line. Minus flags, and these can be, we'll see there are lots of them, and you will have a series of files, and those files can be .c files, they can be .o files, they can be all sorts of other files as well. There are other types. Now at the bottom here you'll see that there are in fact a number of different phases. Pre-processing, which is essentially text editing. It's a lot of very complex text editing. But what it does mean is what the compiler sees is very, very different from what you typed in. And it's worth remembering that. Now the output is actually humanly readable, but rarely human understandable. And there are lots of hash includes, .h header files, and defines. And pre-processing can be used in all sorts of ways to really localize the compiler to the specific environment, be that Linux or iOS or Windows or whatever. Compilation itself is just one phase, and that can normally have a number of different iterations depending on the techniques used. And at the end of that, the output you get is either assembler or some sort of intermediate object format. An object format means that it's machine readable. Now if it's assembler, that's good, because sometimes you occasionally want to look at the assembler and figure out what it's decided to do, and on really odd occasions you might even want to edit that. If it's object format, you then have a choice, because you then have to try and disassemble that yourself, or play around with it, or just hope that it works. Optimization, which is said is optional, is trying to do a number of different things, and some of those are contradictory. So sometimes it'll be trying to speed up the code, and code that is speeded up may become larger, or it may be trying to trim down the code, which may make the code slower, which sounds rather counterintuitive, but it certainly can have these effects. And quite often you want to be quite careful with optimization, because it can have unwelcome side effects. Now the output from optimization is normally what's called a relocatable object file, and the file at the top here called this file, that is a relocatable object, which is now being linked in prior to loading, which is execution, really. Okay. Now there will be other files which you don't really have that much to do with, other object files which allow the creation of an executable binary. And particularly important from our point of view is startup code, but library files we'll see later on are very, very important. And then at the end of this process, you possibly will get a set of warnings. You may get some errors, in which case you won't reach the end of this process. And hopefully you'll get an executable binary. We're going to look a little at doing this on a Linux machine and seeing what the differences are with cross-compilation and native compilation. Okay, so on our Linux system, we will have a native compiler, and that will normally be called GCC. It can also sometimes be called CC, but that's a link normally to GCC. If I can type. And on our system here, it's running tiny slowly, it's an emulator, and this shows that GCC is there, and that gives a very short summary of some of its commands. If we want to know where GCC is, we can ask the system, and you'll see that it's there's a library and there's also the binary. And if we look in /usr/bin, you'll see that there's a number of GCCs knocking around, various tools, which we'll discuss later on. Okay, now I'm going to create very quickly, using the wonderful Olimex, a very, very small program called test.c. And oops, well, again, as I said, I'd hope if I could Control X1. Okay, now this is a very uninteresting program. It returns no value and takes no parameters. It's got one variable called I, and it sets I equal to 10, and then its work is done, so it terminates. So I'll save that program. So here we've got a program, possibly one of the least interesting programs you will see, but nonetheless it is executable, or it can be executable. And this means that the program itself is quite useful because it has no input or output. At the moment we don't want to deal. Input and output are quite tricky. It requires knowing all sorts of details about the hardware off chip, essentially, and we just want to know about the CPU and the instruction set. So what I'll do is I will compile the program using GCC, and I'm going to use a flag, and I'm going to put the output into something called test686.out, and then the file itself, which is test.c, and nothing to report, it's done it. And if we ls, we'll notice we've got test.out, and the system already knows that test.out is slightly different. So if we say file test star, it says one of them is all of this stuff and the other one's just some C programs. Okay. Now, as we can see from this, it says that it's something called an ELF, which I'll explain in a little bit. It's 64-bit. It's got least significant bit executable, and it's Pentium. And the rest of this we'll ignore for the moment, but I will explain later on. Now, this program can be executed. So if I type in test686 out, it executes. It's very boring. It sets I to 10 and then stops. So now I could compile this and I can run this program on an ARM machine, but I can't run this version because it's Pentium. So what I need is a cross compiler. Now, if I type in ARM and I don't get to the cross compiler, what this means is my path is incorrect. And if I type in echo $path, which is where it looks for these things, it's not looking in the correct place. Now, because I installed the cross compiler, I know where they are and they're here. So I could compile this by typing in the full path name So just for example here, and there we are, different output, and this is the ARM cross compiler. Now we don't want to have to type that in every time, so if you get in this situation, and it is possible to not have the path names because we're using make files most of the time, but it is worth knowing how to do this. So what we can actually do is we can edit this path variable and add the path to our command line. Now, the way in which I'll do this is by editing bash rc file. Get rid of the nonsense, go to the end of the file, and I'll input path equals the contents of path plus, now I need that path name. Now, an easy way of doing this would be to ask Emacs to look for me, and there they are. So what I can do is now cut and paste that. The colon's necessary so that it knows to separate each one out. So now I'll save that, and the bash rc file is executed every time I execute a shell, so a command line. Now the problem is since I've edited this prior. This happened after I entered the shell, so I need to actually re-execute the command as if I were or I could just kill the shell and redo it, but this is sort of simpler. And now if I say echo $path, we see it's now got a bit of command line that we wanted. Okay, now I can now type in arm -none, and we'll see we've got GCC there. So if I now say -o test arm .out and then test.c. Now this gives us a warning. It's only a warning, so it hasn't not loaded, but it's saying, oh, I'm not sure where to start, so I've decided to start here, and that may or may not be sensible. And that's really because we're going for another architecture. GCC didn't have this problem because GCC on the native machine can execute. It knows where things start. If it didn't, it wouldn't be able to execute. Whereas the cross compiler itself is a Pentium binary, okay, and it not necessarily knows where these programs are going to start because it's probably cross-developing for lots of different boards. Now if I do file test star, we've got three things. Our C program, we've got our Pentium, and we've got test arm. Now it's an ELF, exactly the same. It's 32 bits, not 64-bit. It's least significant bit executable, but it's ARM. Okay. Now, the other important thing that comes up, and we'll find out more about this later on, is this one is dynamically linked and this one is statically linked. And nearly always in cross development, your programs will be statically linked, okay? Which means that everything is inside them. So quite often they seem quite large, whereas these ones can seem quite small because they don't actually achieve their full size until they're executed. Now, as we saw, we could run test 686.out. If I try to run test arm, we'll find it just says it can't do it. Now, you'll find on different machines this will work differently. Some will crash. It will actually cause quite a problem, and it will do something called a core dump, which is basically the computer crapping itself. So you'll get different reactions on different machines depending on how they've been set up. Now, there is an ARM emulator called QEMU, Quick Emulator, and if that's running, it will kick in and try to interpret the instructions. So it is possible it could execute it. The chances that it actually have our board, the Olimex board, layout within it is pretty remote unless we're to set it up. Okay, so we've now got these two different files. We've got an ARM, which can be executed on an ARM board, and an x86, which can be executed on a Pentium, and as we've seen, is executable. Now, just a little bit of backtracking. We've seen up here all of these parameters that can be given, these flags that can be given, and it's worth figuring out where these come from and how to deal with them. Now, the easiest way is to use the man command. So if I type in man-gcc, and it then gives you the list of options, okay? And the one that we used is an output option, and it comes somewhere along here. In fact, it's here, -o, out file. But there are lots of options, okay? Lots and lots of options. So here's some just for ARM computers. And lots of the people who write compilers possibly don't have the greatest of social lives. They do seem very obsessed by dwarves and elves and things like that, but there you go. But it's a very, very good compiler, okay? And it's used industrially, it's very widely used and widely respected. So it is worth, even though this does seem somewhat over the top, and some of the options you wonder who would actually do these, they are all very important. Okay, so there are lots and lots of them, and this goes on. Now, manual pages are not tutorials. They're really for people who know more or less what it is they want to do, but just can't quite remember or can't remember the syntax. If you want to do something a bit more gentle, it's probably better looking on the internet and finding some gentle tutorials on these things. Okay, so, and particularly when we come to looking at the make files, we will look a lot more at some of these flags. Okay, now the other thing that we can do is, because we've got an executable, and if we try to look at the executable, if I said cat test 686, I'm not entirely sure what will happen when I do this, but it'll probably screw the screen up good and proper. So it's just, actually weirdly, you can see it says elf, that's about it. And then there's lots of names of dummies and frames and offset tables and stuff like that. And almost undoubtedly be a dwarf in there somewhere as well. Now, we can't really look at this because it's binary, it's machine readable. However, we can disassemble it, and if we use objdump, -D, capital D for disassembly, and then do test 686.out. There'll be a lot of output, so I'll pipe it through more. And here now we can see a set of instructions, and the first one being something called bad, which normally means generate an exception, but anyhow. And eventually, if we go down here, there's lots and lots of setup, lots of code that we appear not to have anything to do with. There's a bit obviously called start, which looks quite important. There's various library starting codes and initialization. And then sooner or later it gets to main, and there's a bit of code there that somewhere has managed to set 10, there it is, there's 10 into our variable, which is an offset on the stack. Okay, and then there's not a massive amount of code. It's fairly small, really, but as these things go. We can even ask it how big it is, and it tells us how big the actual program is, quite small, really. And this is the executable code known as text, the data, and the runtime data. Now you might wonder, why has it got 544 bytes of data when in fact we've only declared an integer? And a lot of that is to do with system work. The system needs these things. Now, if I try and obj dump the test R, it says quite randomly it can't do it. It doesn't know what the architecture is. So we now need to use the obj dump with the cross development tools. These tools are known as bin utils, like size and obj dump, and there are all sorts of other ones, and they're very, very useful for messing around with code, getting code to work on machines. So test arm.out. And it's different instruction sets. Okay. But again, we can see there's these various things called frames, and main is there. There's a bit of initialization. It doesn't have much setup, okay? But that's basically because it doesn't know what the machine is. It knows what architecture is, but it doesn't know the machine. Whereas the Pentium did actually know the machine, okay? And so fairly small, but that's everything. The other one didn't have everything in it. So if we now do size test arm.out, oops, -T, but there we go. And there you see it's pretty small, 180 bytes decimal. Okay. So, what have we learnt here? Well, firstly, that you do need to be able to use the command line. You will be using make files, and that's going to be the subject of the next seminar. However, you will need to use the command line, and sometimes rather than continually rerunning make files, you occasionally need just to test a particular command on the command line. So getting a certain fluency with the command line is a good idea, because IDEs are very useful in certain circumstances, but they are quite limiting. Okay, there are, you know, it's, I don't know, like trying to surf wearing a sort of diver's bell or something. That, you know, you'll be very well protected, but you won't be a very good surfer. Okay, so you need this sort of agility that the command line gives you, and it will really, really pay off. Now, at first, you'll find, you know, that you don't know many of the commands, you don't know much what's going on, so you use the man command and get used to reading these, because they're not really written for humans. As it says here, this information is mostly useful for programmers who are working on compilation tools. So, this is fairly technical information, but which you need to know. Now, coming out of a computing degree, if you don't know stuff like this, then your degree has been a bit of a waste of time, I'm afraid. Okay, so that's enough on compilation tools for the moment. What we will look at later on is make files, and particularly how our programs are executed. Okay, thank you for listening.